As you've already been reminded, BQ2, which was issued last week, is due tomorrow. And if you want to place yourself in best position to understand and follow along with the discussion in tomorrow's discussion class gathering, which is on section 22.4, which lays foundation for everything you're going to do in chapter 22 on electrochemistry, read it and study it in advance. And that'll be the topic for consideration tomorrow. We'll begin with such today. Last time we showed you that the best way by far to get at oxidation number assignments is by Lewis structure analysis. Now, more fundamentals of electrochemistry, which is the study of redox reactions. And a redox reaction is most simply studied or analyzed as a combination of two parts, oxidation and reduction. I expect you've all heard this before. Functional definitions: oxidation, capo and parenth, abbreviational reference. Half reaction in which atomic oxidation number increases. ON for oxidation number, and arrow up, increase. Reduction, half reaction in which atomic oxidation number decreases. So in developing equations for redox reactions, we will always go through the process of examining the reaction system to find out what's oxidized, and with that we'll write the half reaction equation, the equation for the half reaction which shows oxidation. Then we'll look at the system again and see what's reduced, and then we'll write the equation for the half reaction that corresponds to reduction, and then we'll get the net redox reaction by putting the oxidation half together with the reduction half. This process is called coupling. We'll illustrate such today. Before we get on with the illustrations, take a look please at table 2, which is on pages 4 and 5 in the chapter on electrochemistry. This table is reading just like an acid-base table, practically speaking. Except that in the acid-base table we didn't have any reaction equations. Here we have a collection of half reaction equations. You remember in the acid-base table the acids were listed in order of increasing strength in the acid column, and the corresponding conjugate bases of these acids were listed in order of increasing strength top to bottom. Bottom to top for the acids, top to bottom for the bases. So in this half reaction table, the reducers are listed in order of increasing strength from bottom to top, which means when you look at this table, the strongest reducer listed in this table, this is not a comprehensive table, is lithium solid. That's the reducer in half reaction number 1. And the weakest oxidizer listed in this half reaction table is the conjugate oxidizer of the strongest reducer. Is that surprising? Just like in the acid-base table, the weakest base is the conjugate base of the strongest acid. Here, the weakest oxidizer is the conjugate oxidizer of the strongest reducer, which means lithium ion AQ. So when you go to the very bottom of this table, which I think is half reaction 44. I don't remember how many half reactions we got in this table. Is it 44? 45? Was it?
45.
45. Okay, I didn't remember the number because I keep adding to this table. The bottom half reaction in this table, half reaction 45, shows reducer fluoride ion being oxidized to the conjugate oxidizer of fluoride ion, which is elemental fluorine, which is the strongest known oxidizer. So you shouldn't be surprised that the strongest oxidizer in this half reaction table is the conjugate oxidizer of the weakest reducer. That's fluoride ion aqueous. So I hope again this shows you how this table reads just like the acid-base table. Now then, we'll also learn from the acid-base table that when an acid reacts with a base, which always gives us a different product acid, different from the reacting acid, and a different product base, different from the reacting base. If the product base is a weaker base than the reacting base, if the product acid is a weaker acid than the reacting acid, we can expect that reaction to proceed to a large extent. And now when we got to chapter 21, we learn that for any such reaction, delta G0 will be a minus value. The K, the equilibrium constant for that reaction, will be a K value that's bigger than 1. And vice versa. If the product acid is stronger than the reacting acid, then delta G0 is smaller than 1. The K value is less than 1. I mean, delta G0 is plus, pardon me. The K value is less than 1. And we expect that reaction to go to a small extent. So regarding coupling half reactions, to get a net redox reaction, look at the table. Pick any two half reactions. I don't care which. Any two half reactions. If we are of a mind to write an equation for a redox reaction which will operate spontaneously and in so doing deliver usable electrical energy, so we can power a light bulb or something like that, you will take, of the two half reactions you've selected, you take the half reaction of lower E0 value. You see the E0 value? The unit on E0 is V volts. Volts is a measure of potential, tendency to go. So from an E0 standpoint, a redox reaction which is spontaneous has a positive value for E0. Of course, a negative value for delta G0, but a positive value for E0, because it says it has a tendency to go as written. Okay? So back to this coupling business. Pick any two half reactions. In order to make an electrochemical cell which will liberate usable electrical energy, which means it'll have a positive E0 value and a negative value for delta G0, you take the half reaction of lower E0 and take that half reaction, write it in reverse. And when you write it in reverse, you change the sign on its E0 value. And then you make adjustments of coefficients on the two half reactions as necessary, so that when you add them up, all electrons cancel. Because as we have recognized, you cannot run a reaction in which electrons are net reactants or net products. Because if such a system was stable, then Horvath would open up his electron store and all that stuff that we've told you about before. But that's not the way nature is. Okay? Now then, first, let's take a look at illustrations of oxidation and reduction and how, from these illustrations, we could write the equations for the half reactions, and then how we'd couple these half reactions to get a net redox reaction for which E0 is positive and delta G0 is negative. A spontaneous redox reaction system. What we're going to do is just like you did in Assignment 5, Part 1, 45 laboratory. How many remember doing that? You started by looking at a video. In the video, there was a famous actor. Kind of looked like me, because it was me. Okay? Remember looking at the video? Now, the demonstration, which I did in the video, we're going to repeat here. It's a redox reaction of sodium with water. It's a reaction which I'm sure just about every student in the class would love to have the opportunity to carry out himself or herself. They'd get the largest possible chunk of sodium, beaker full of water, throw this sodium in the beaker full of water, pow, and say, oh, that was wonderful. I had a great deal of fun in chem lab today because I blew the hell out of everything. But we are not entirely ignorant of students who are of a mind to behave in this fashion. We are aware of such individuals. So instead of letting students do this, we have the famous actor do it instead. The famous actor will now repeat. And then after we do this, we will show you the fundamentals of what goes into developing a table, like Table 2. First qualitatively, and then quantitatively. How do you get the E0 values? Okay? Now, one more comment before we proceed with the demonstration. In order to get E0 values, you remember our reminder to you in discussing stuff in Chapter 21 about defining a reference standard when we want to get thermodynamic information tabulated for reactions which are studied in solution? Remember that? You remember the reference? Forming a solution which has a pH of 0.00, which means the hydrated proton is present at a molarity of exactly 1. Has a delta G0 value of 0. Delta H0 value of 0, delta S0 value of 0, and a delta, and not delta, but an E0 value of 0. Look at the table. See if you can find the half reaction to which I am referring. It has the title Standard Hydrogen Electro. Do you see it? What's its number? What is it? 29? It's the half reaction which has an E0 value of 0. It corresponds to the oxidation of elemental hydrogen to hydronium ion under standard state conditions. 1 molar for solute concentrations. So, if hydronium ion is present under standard state conditions, it's 1 molar, which means the pH is 0.00. Okay? And all the other E0 values you see in this table are measured relative to that assigned reference point value of 0 for the oxidation of hydrogen to hydronium ion at pH 0. All right? Now let's have some fun. First, unlike what you folks did in 45 laboratory, I have here a far more elegant conductivity detection device. See how elegant this is? A light bulb screwed into a socket. We connected electrodes to the light bulb so that the electrodes are long enough to reach into solutions whose conductivity we wish to test with this fancy gadget. In the beaker presently I have deionized water. And plug in a power source. Note that when I bridge the leads, electrons can flow from one electrode to the other, and in so doing pass through the filament of the light bulb, and the light lights. Now you also learn in 45L, if a solution has a fairly high ion concentration, it's a good conductor. Because a current is nothing but a stream of charged particles. Doesn't have to be electrons. Ions. Perfectly good example of a current. A collection of ions flowing in a stream. I immerse the leads into our deionized water. No light bulb glow whatsoever. We're not surprised at this, because this is, of course, a very crude conductivity detection device, and the concentration of ions in deionized water is pretty damn small. Total ion concentration is 2 times 10 to the minus 7. Remember that? Now, as part of this demonstration, we also want to observe if the reaction we run corresponds to the formation of a basic system. So, before we do the investigation, I'm going to put some phenolphthalein in our deionized water, just to see if the phenolphthalein addition causes the light bulb to light. Nope. Still no current flow. Now I'm going to unplug the light bulb while we get on with the chemistry part of this demonstration, because if I accidentally bridge the leads with me, I don't want to have fried Horvath. Now, I have here in this small Stoppard Erlenmeyer flask some stuff which bears the symbol Na. Natrium. You're all familiar with natrium, aren't you? The old Latin name for sodium. Did you ever stop to wonder where we get all these, where we get so many symbols which in no way correspond to the name of the stuff? How the hell is Na sodium? How is Au gold? It comes from aurum, the old Latin name for gold. It's like natrium is the old Latin name for sodium. Okay? Now then, got some Kim wipes here. I got some sodium chunks in kerosene. Whoa! Nice big piece of sodium. Usually the bigger the piece of the sodium, the bigger the boom of the demonstration. Students like that. Teacher gets scared. Teacher has to run away. When I sat in your shoes at the University of Toledo, fall 1960, in my general chemistry class, my lecture instructor was the head of the department chair. And he had a big stick of sodium. Okay? And he had this demonstration all ready to go. And he cut off a little piece of the sodium in order to do the demonstration and made a very, very interesting error. He took the little piece of sodium which he cut off and put it back in the kerosene and the big piece in the water. And said duck. And I mean, it went boom. It was really dangerous. Fortunately, no one was hurt. The only thing that got bruised was the ego of the instructor. He was so shaken by this, he just called off the class. There were little bits of burning sodium all over the place, because the concussion of the reaction blew this stick apart. Now, if I were to cut the sodium freshly you would see that the sodium metal itself has a very shiny exterior surface, but this does not. Because what you're really looking at is sodium oxide or sodium peroxide. Because this stuff reacts immediately with oxygen in the atmosphere. But if I cut it for a second, you'd see a very shiny surface. You might recall that sodium is capable of showing the photoelectric effect. You remember that in 2045? Let me make sure my microphone cords are not wrapped around any of these things, because when I drop this in the phenyltoluene containing deionized water, then I want to get the hell out of the way. Take note that the phenyltoluene is doing its thing. The sodium swims around at the surface because it's less dense than water. Can you see the sodium shape is essentially spherical? Because the heat of the reaction has caused melting of the sodium. It has a low lattice energy. And do you also, does it appear that a gas is being liberated by this reaction? Well, I guess we're not going to get any explosions. Too bad. But at the minimum, you see that the reaction is quite vigorous. It's not uncommon for this reaction to burst into flame, because the gas product that's produced is highly flammable. We'll talk more about that in a second. All right. I can now return. Back to the conductivity investigation. Power's on. Again, if I bridge the leads, bulb glows brightly. And now we see that the solution which has resulted is a good conductor. What does that mean? That means the reaction which we just ran did what? Did what? Made ions, you betcha. Now, again, I'm going to pull out the plug. Now let's talk about the chemistry which took place. In 2045, when you paid attention to valence electron configurations, which is arguably the most important periodic property of any atom in the periodic system, you likely learned, I expect you did, that the only chemistry which the 1A metals ever show is to lose one electron per atom when they react, and in so doing, attain an electron configuration, a valence electron configuration, which is isoelectronic with that of their nearest neighbor noble gas. I like the way that flows along. Nearest neighbor noble gas. Sodium with 11 electrons becomes Na+, and now electronically is isoelectronic with neon, which means isoelectronic means has the same electron configuration as. And that's where the chemistry of sodium stops. Because as Ne configuration, it is extremely stable, you betcha. If we did this with K, K would lose one electron per atom, become K+, and become isoelectronic with argon. And if we did this with K, would we expect the reaction to be even more vigorous? What I'm asking is, do you remember from 2045 chemistry how the first ionization energies of Na and K compare?
Na superior to K.
Which one has the lower ionization energy? Sodium or potassium?
Potassium.
Lower ionization energy. Means it's more easy to ionize. Potassium. Ionization energies increase as atoms get larger or smaller?
Smaller.
Ionization energies as atoms get smaller. So, ionization becomes easier to achieve as atoms get larger, because the valence electrons are further from the nucleus for the larger atom. So even though Potassium has got 19 total protons, and sodium only 11 total protons. Potassium is easier to ionize, because that valence electron is further from the nucleus than the valence electron for sodium. I trust you talked about this in 2045. There's a huge difference between effective nuclear charge and total nuclear charge. Did you discuss that in 2045? Huge difference between effective nuclear charge, that's the actual attraction exerted upon a particular electron in an electron configuration. And the electrons with which we are most commonly concerned are the valence electrons, because those are the ones that account for the reactivity of the atom in question. For potassium, that's a 4s1 electron. For sodium, it's a 3s1 electron. Independent of the fact that there are a lot more protons in the nucleus of K, it's easier to remove the 4s electron than it is the 3s electron. Again, because K is bigger. Well then, if the only chemistry which these 1A family atoms show is to lose 1 electron per atom when they react, we can write this. AQ, because we did this in aqueous media. So in this half reaction table, which we are going to begin to develop for reasons that we shall expound on as we proceed, we'll list sodium in number 1 position. So for our half reaction table, sodium converting to sodium ion is the number 1 half reaction. It will be the half reaction containing the strongest reducer, that's sodium, and the weakest oxidizer, which is Na+, the conjugate oxidizer of Na. Now then, what's the other part of this puzzle? Well, the other part of this puzzle had to involve reaction with water, because all we did was to put together sodium and water, right? So if sodium became positive ion, water had to, in some fashion, get converted to a... If I have neutral species to start with, and in the reaction I make positive ions, is it possible to run this reaction and only have positive ions being formed when I started with neutral species? Could such a system ever be electrically neutral? No. So I have to, in addition to making positive ions, also make negative ions. Now, we also observed that the system became quite red-pink, characteristic of an alkaline solution. And we know that water has the component elements necessary to make what basic species with which we are familiar? Hydroxide ion and? What basic species? Oxide ion, and even H-, the hydride ion. Well, we've reminded ourselves. You are much more likely when you start tearing up water molecules to make hydroxide ions than you are hydride ions, because of the far greater electronegativity of oxygen. So we can expect that water will be the electron collector, since this half reaction is the electron liberator. And that the basic species which is produced is the negative ion hydroxide ion, which maintains electric neutrality for the system, because this thing produced positive ions, and is responsible for causing the system to become this red-pink. Now, I had hoped, given that this usually happens, but it didn't this time, that the gas which is produced from this reaction would ignite, because there will be some atmospheric oxygen in here, because there's air above the system. And the heat of the reaction is usually sufficient to get this flammable gas to ignite. Well, if I am going to stipulate, because it's awful difficult to see that a colorless gas is being produced, unless the gas is being produced underneath the surface of the solution, so you can see bubbles, but we didn't see any bubbles here, because the sodium, maybe I'll have to put an anchor on sodium when I do this next time. Make it go down so we can see bubbles. So whatever this gas or gases that are produced had to be derived from water. This is no gas, this is no gas. And we know at a glance that hydrogen and or oxygen are gases derivable from water. So let's write down H2 gas and or O2 gas. Question. By oxidation number analysis, is it reasonable to look at this half reaction, which involves water collecting electrons? Is it reasonable to conclude by oxidation number analysis that the gas produced cannot be oxygen? Is that a fair conclusion based on oxidation number analysis? Well, water molecule. Oxidation number determination. Parcel electrons. Play the game we showed you last time. To see oxygen is -2 and each hydrogen is +1. These again are oxidation numbers. They're not charges. And in any element, what is atomic oxidation number value? 0. How the heck could I give electrons, which are minus, how could I give electrons to water, which contains oxygen in the -2 oxidation state, and in so doing generate molecular oxygen, which has got oxygen in the 0 oxidation state? That ain't possible. But what about hydrogen? Molecular hydrogen, oxidation number for hydrogen atom 0, and in a water molecule, oxidation state hydrogen +1. So that tells me the gas I produced, which is flammable, is hydrogen. Is oxygen flammable? Is oxygen flammable? Yes or no? Yes. It is not. It's a combustion supporter. If you strike a lit match and place it in oxygen, the match will burn away quicker, but that's the end of it. Be careful with lit matches around hydrogen. Of course, the hydrogen would have to be mixed with an oxidizer. But a hydrogen-oxygen mixture, whoo-hoo, be careful about that. You familiar with the dirigible Hindenburg? That shows you what happens when a hydrogen-oxygen mixture is caused to react. Away went the Hindenburg. Now then, let's look at this statement which we have written. Is this an equation? That's these damn textbooks talking about balancing equations. I don't know what the hell kind of language that means. That bastardization of the language has even crept into dictionaries. I won't accept that. Equation by definition means balance, damn it. So don't talk to me about balancing equations. If I write a statement and it's not balanced, it is not an equation. And I will not accept anybody telling me that I should balance chemical equations, because that means I'm dealing with a balanced statement. So phooey on that bastardization of the language. Just like hydroxide is HO minus. I don't give a damn about all the tradition and all the stupid people that have written it OH minus for so long. That practice stops in this place. If we're going to successfully communicate to you, we have to be sharp, clear, and precise in what we say. And if we're sloppy and careless in what we say, or in the definitions which we invent, how could you possibly learn? So I have great patience with students. But teachers who violate these rules of common sense, as far as I'm concerned, I don't know what the hell they are, so I'll strike teachers. They ain't. They're bad people. Evil. Just like textbooks who do this junk. This is not an equation. I call it a skeleton. Because it does contain the correct formulas for the reactant and the products. But since it is not balanced, it is not an equation. What can we do to turn this into an equation?
opposite.
I'll accept that. Now, how so?
Adjust the coefficients.
How so? Tell me what to do. I appeal to you for your assistance. Well, at the moment, we'll balance it by the first method taught to you in balancing skeletons. It's called inspection. You take a look at the statement, and as things presently stand, you see more hydrogen atoms on the right than you have on the left. If you count up all the hydrogen atoms, which are components of the species involved. Okay? So I got to have more of these than one. All right. So I'll go to 2. And then I will see at a glance, I hope, since I'm multiplying this by 2, I not only doubled the number of hydrogen atoms under consideration, I also doubled the number of oxygen atoms under consideration. If I put 2 in front of hydroxide ion, I got a material balance, don't I? So what multiplier do I have to put here to have an equation? 2. No big deal. And now, coupling. If I want to put this half reaction together with this half reaction to get an equation for the net redox reaction that we just ran, I can take this half reaction as it is written and divide it by 2. Or I can take this half reaction as written and multiply it by 2. Doesn't really matter, but I'll do this because I, if possible, choose to avoid fractional coefficients. Nothing wrong with them, but they're a little bit messy in bookkeeping. Because when I multiply this statement by 2, it shows the liberation of 2 moles of electrons, and this, which requires the consumption of 2 moles of electrons, means when I now add these things as written, there will be no electrons in the net reaction. So I'll have this as my net redox reaction. And then I can pay attention to more fundamental electrochemistry nomenclature. In this redox reaction, what is the reducer? Sodium. The reducer is the component of a redox, the reactant component of a redox reaction, which is responsible for reduction. But what does the reducer itself experience? Oxidation. Because sodium, in functioning as the reducer, in reducing water, converted to sodium ion, the oxidation product. The stuff produced by oxidation. Whereas in this system, water is the oxidizer, which means water is responsible for oxidation. But in accepting this responsibility, the oxidizer, water, gets reduced. What did it get reduced to? Hydroxide ion and hydrogen. So these are the R products. Now, to add this water half reaction to the table we are trying to develop in a systematic fashion requires me to take this half reaction and write it in the opposite direction. Because I'm going to make a table where all the half reactions written are electron liberators, just like the table in the book. We could write them all as electron consumers, wouldn't make any difference. But I'm writing them as electron liberators. And do you think, from what we have done, it is fair to say that as a reducing half reaction, this half reaction is certainly stronger than this half reaction? You think it's fair to say that sodium as a reducer is a hell of a lot stronger than hydroxide ion hydrogen? I guarantee if you keep shoveling sodium into this, you're never going to get this thing to come to equilibrium. If you keep shoveling sodium into this, you will always have consumption of sodium and production of hydroxide ion and hydrogen until either all the sodium is used up or all the water is used up. This will never come to equilibrium. Unlike acid-base reactions, redox reactions usually have K values which are damn huge. Practically speaking, most redox reactions are like one-way streets. Not much equilibrium of consequence. Now then, we ran out of time, but let me remind you in brief about the part of this investigation that I had hoped to do today but didn't get to do, and that is a takeoff on what you did in 45L. See this? Zinc, zinc ion, copper, copper ion. Very quickly. Piece of zinc, zinc strip, copper strip. What would you do if you are given the responsibility of using copper, copper ion, zinc, zinc ion, and told with these materials and these materials only to make an electrochemical cell which will deliver usable electrical energy? Well, you inspect these materials and you recognize that zinc and copper are each potential reducers. If they are going to get oxidized, then I can well expect to oxidize this to this or this to this. But if I don't know anything about zinc and copper as reducers, then I don't know how to build a system because I don't know which one is the stronger reducer. But I know since they're different, one of them's got to be stronger than the other. So here lays the essence of what you did in 45 laboratory, assignment 5, part 1. Do you remember what you did? You took a particular possible reducer, like zinc, and mixed it up with the conjugate oxidizer of the other possible reducer. Sounds like double talk, doesn't it? You take the zinc and mix it with copper ion. And at the same time you take copper and mix it with zinc ion. Because if zinc is a better reducer than copper, then zinc can reduce this. But if copper is a better reducer than zinc, then copper can reduce this and zinc can't reduce that. So, all you need to do is to take some copper sulfate solution, which I have here, and some zinc sulfate solution, which I have here, since these contain copper ion and zinc ion respectively. Got these from the laboratory. And in the solution containing the zinc ion, I'll put my copper strip. Now if I allow this to stand for a good long time, I'll not see anything take place. But watch what happens as I take this freshly sanded, abraded zinc strip and put it in contact with copper ion. That's all it took. And now what I have formed on here is a deposit of copper atoms. They form so rapidly that they don't show the characteristic bronze color, because I have not yet had a chance to develop a copper lattice of consequence. If I leave this zinc strip in contact with the copper ion for a minute or so, you'll see this becoming characteristically bronze, the color of copper. So now I know zinc is the stronger reducer between zinc and copper, and hydrated copper ion versus hydrated zinc ion. Which is the stronger oxidizer? Copper. Copper ion. So there's my system. I give zinc the opportunity to give electrons to copper ion, and in so doing produce copper and hydrated zinc ion. Pick it up from this point tomorrow and then Wednesday.